Hello, my name is Óscar Sanchidrián. I'm a student of Mechanical Engineering and Industrial Design in group DM201. Today I'm going to talk about robot dynamics. First of all, what are dynamics? Dynamics are the branch of physics that study the relationship between forces exerted on objects and the effect they have on their motion and trajectories. In our context, robot dynamics serves as a tool to predict and simulate the motion of robots and to develop algorithms that help us control their motion. Today we'll go over what notation is used in robot dynamics, what is the model of a robot, and the main algorithms that are used in robot dynamics. First of all, notation. The main difference is that 6D vectors are used. They are vectors, 6-dimensional, which contain both the linear and angular aspects of every variable that we use. Because of their compactness and because they are easy to use and implement in computer software, they are the ones we use here. The usual vectorial operations are used, such as addition or multiplication, and as a conclusion to this small interlude, we have to state the spatial equation of motion, which is a very compact equation that contains both the Newton and Euler equations of motion. Now, next on our list is a model. Models are a simplification of reality that we use in calculations because they are simple yet accurate, which makes all the processes much more faster. The rigid body model of a robot is made up of 4 parts. A connectivity graph, which is a drawing where the nodes stand for the rigid parts and the arcs that connect the nodes stand for the joints in the robot. There are 2 very important terms. A kinematic tree or closed loop mechanism is a connectivity graph in which any arc is not crossed more than once. And on the other hand, we have kinematic loops or open loop mechanisms. Next, we have link geometry that describes the position of every part. Then we have link inertias that describe the center of mass, and rotational inertia of the different parts. And then the joint model that describes the different connections between the different links and joints. Finally, we can explain the algorithms that are used. Kinematic trees are the base of these algorithms as their dynamics are much simpler than those in kinematic loops. There are 4 algorithms for kinematic trees. The first is the recursive Newton-Euler algorithm. It calculates the inverse dynamics of a fixed space in a kinematic tree. In simpler terms, that means that it calculates the necessary torques and forces we need to apply in the robot to obtain the desired motion with acceleration, speed, for whatever purpose that we need. There are 2 variants of this algorithm. There is one that uses link coordinates instead of absolute coordinates, where a reference frame is made for every joint, and another one that uses 3D vectors. Although we did say earlier that they are not as handy in robot dynamics, in this case some terms are cancelled out, so it's actually faster. The way it works, this algorithm works is that the speed, force, and the equation of motion are calculated, and then we obtain the necessary torques by multiplying the motion matrix by the spatial force. The next algorithm is the articulated body algorithm. It calculates forward dynamics, which means simulation of the robot depending on what variables are acting on it. And its working principle is that there's an equation that connects the accelerations to the forces. Third algorithm is the composite rigid body algorithm. Again, it calculates the forward dynamics, but also the joint space inertial matrix, which is a matrix that is used to analyze processes and map accelerations. The way it works, it solves a linear equation for a kinematic tree with the recursive Newton-Euler algorithm, and then it calculates the joint space inertial matrix. However, if the number of the branches in the kinematic tree is 0, then the joint space inertial matrix is 0, and it makes the calculations much faster. Last algorithm is the operational space inertial matrix algorithm, which gives us a set matrix, which is used to connect task accelerations to task forces. There are 2 versions, one for robots with a small number of degrees of freedom, in which we calculate the factorization of the joint space inertial matrix and then obtain the operational space inertial matrix from it, and the other version in which we use the previous algorithm to calculate the inverse of the operational space inertial matrix. With this said, we must also state that there are algorithms for open loop mechanisms, but they are not used as much because they are a bit more complex. However, In this they are more complex because the number of degree of freedoms can change and forces sometimes are undetermined. However, because in their equations sometimes some terms can be calculated with kinematic trees and others can be simplified to zero, calculations are easier than we would expect it to, and we just have to calculate two variables to control a robot. In conclusion, I've gone over what are robot dynamics, what's the notation used, in which 60 vectors due to their compactness are used, what's the model of a robot and the importance of kinematic trees and kinematic loops, and the four main algorithms that are used to control kinematic trees. This chapter provides us a brief insight into what are robot dynamics and gives us the necessary tools such as notation, math, and algorithms with which later we can enhance and expand our knowledge. Thank you.